In this short video, we're going to look at the origin of the solar system. The solar system is made up of the sun, the 8 major planets, and a bunch of smaller objects. The theory that explains how the solar system formed is called the nebular theory. Here, you see a photo of the Orion Nebula. Our sun and the solar system formed from a similar nebula. A nebula is just a cloud of gas and dust in space. This is a picture of part of the Eagle Nebula, called the Pillars of Creation, in the constellation of Serpens. But these clouds aren't like clouds in the sky. They are immense. The entire nebula is estimated to be 70 by 55 light years in size. Remember, a light year is about 6 trillion miles. Star and planet formation within these clouds takes millions of years. So how do we think we know how star formation works if nobody can live long enough to see the entire process? Here's an example. In this picture, you see a baby, a young boy, a young man, a middle-aged man, an older man, and a very elderly man. These are all representing one person at different stages of his life. Now what if I mix up the pictures? Could you put them back in order? Of course you could. You can tell how this man aged over time just by seeing a few snapshots of him throughout history. Now back to the nebular theory. These are a few sketches of various stages of star formation. Can you tell in which order they must have occurred? Hopefully so. Image 4 must have come first. This is the cloud of gas and dust we call the nebula. What should come next? Next should be image 1. As gravity begins to pull material together, the cloud begins to spin and flatten. Imagine this like someone making a pizza crust from a lump of dough. As they chuck it up into the air and spin it, it flattens out. Next comes image 5. We see a blob that will become the sun forming in the middle. This forms because gravity is pulling the material together in the center of the gas cloud. Image 2 is next, where we start to see planets accreting or building up from material farther out in the nebula. They aren't fully formed planets yet. We call them planetesimals or protoplanets at this stage. Image 6 is next, where the sun is now shining. We'll talk more about that process in Unit 3. The planets are mostly formed, and there's just a little bit of gas and dust remaining. The final stage is seen in image 3, the completed solar system, where all the remaining gas and dust has been collected into the sun or planets. Here is the same process in a more realistic looking picture. Again, you start out with the cloud of gas and dust called a nebula. As gravity begins to pull material together, the cloud begins to spin and flatten. This is called the protoplanetary disk. The blob in the middle will become the sun, though it isn't actually shining at first. If you've ever played with a Hoberman sphere, you understand how this works. As you rotate the giant sphere, it collapses into a tight ball. The process of accretion continues to occur, bringing more material into the sun and beginning to clump up other bits of material into small planetesimals that will eventually combine to make the planets. The gaps in the middle of the disk are created as planetesimals orbit the sun, sweeping up the gas. Each orbit, the planetesimals enlarge from the additional gas and dust they have collected, and eventually all the remaining gas and dust will be swept up by the sun or the planets, leaving the finished solar system behind. Here is an artist's conception of a protoplanetary disk on the left. Again, that's what we call that second stage after the nebula begins to spin and flatten out like a pizza crust. These gaps in the dust would be areas where planetesimals are orbiting. Baby planets sweeping up material and colliding until all the material is combined. On the right, we see actual images of these disks and their young suns in the middle taken by the Hubble Space Telescope. Because all the planetesimals were orbiting in the same plane of the protoplanetary disk, we can actually tell where our solar system's protoplanetary disk was. It was along the plane of the ecliptic, and that's why we still see the moon, sun, and other planets following this trail across the sky. Smaller objects, like Pluto, are often not directly along the same path, as they are more easily gravitationally disrupted into other orbits. But this process of accretion is not fast. It can take millions of years for all this material to collect together. In our own solar system, this process started about 4.5 billion years ago. Planetesimals collided, remelted, and differentiated to form layered structures. This process continued for about 1 billion years. Here's another image illustrating these two important processes, accretion and differentiation. Accretion is just smaller things coming together to make bigger things. Imagine a small child smashing multiple balls of Play-Doh together and making one large ball. Smaller planetesimals would be pulled together by gravity. When they collide and stick together, larger protoplanets form. Some of these collisions were very violent. Heating from these collisions and radioactive materials within the young planets caused them to melt either partially or completely. Heavier materials sink to the middle, making the cores of planets, while lighter materials layered on top, making the mantle and crust material. If you've ever seen water and oil poured into the same container, you've seen this happen. The heavier water sinks to the bottom, while the lighter oil floats on top. This process of planetary bodies separating out into layers is called differentiation. This is an artist's conception of what early Earth would have looked like, literally hellish. On the right, we see an image of the Earth very early on. The bright spots you see are where impacts were constantly occurring, and you can see lots of rocky debris still around the planet. Very early Earth would have been a mostly melted ball of rock and metal, continually being impacted by more pieces of space debris. No life could have survived on the planet during this phase. On the left, we see much less of this debris around the Earth, though some remains. This is Earth in a later stage. Most of the surrounding debris has already collided with and been combined in with the planet. You also see a cutaway section showing the core and mantle material, illustrating that early Earth was already differentiated at this point. The gray material here is melted rock as it's cooling, forming an early crust. But the process isn't exactly the same in all areas of the nebula. The sun is in the center, and the material in the disk cools as you move away from the sun. The sun swept up the majority of the gas in the inner solar system, leaving only rocky and metallic material for the innermost planets, Mercury and Venus. Farther away, temperatures were cool enough for water and water ice to exist on Earth and Mars. Even farther out, substances that are gases in the inner solar system, like nitrogen and methane, can exist as liquids or solids due to extremely cold temperatures where the gas giants are. Finally, we need to look a little bit at scale models. You have 2 assignments to do related to this topic. One involves size scale, and the other one involves distance scale. This image shows size scale. Notice how big Jupiter is compared to the other planets. Notice further how big the Sun is compared to Jupiter. The Sun is so big, you couldn't fit the whole thing on this diagram without making some of the planets so small that they could not be seen. This diagram shows size scale, but not distance scale. In this image, the planets all look about the same distance apart from each other, but this is not true in real life. This image shows the distance between the planets to scale. You'll be making a model similar to this in your next assignment. Notice just how close the inner planets are. Mercury, Venus, Earth, and Mars should all be crammed in here between the Sun and the asteroid belt. We know, however, they are quite far apart since we don't see a giant Mars or Venus in the sky. But they're much closer together in comparison than are the outer gas giants. There is a lot of space between those objects, and that's why they call it space. Here's my terrible joke for today. If the scale model of the solar system were the size of a person, Uranus is right where you'd think it would be, right in the middle. This slide shows a little bit more about size scale in space. In the first image, you can see that Earth is bigger than the other inner planets and is only slightly bigger than Venus. But in the second image, can you see how small Earth is compared to the gas giants? Jupiter's huge. But in image 3, Jupiter looks really small compared to the Sun and bright star Sirius. Continuing on, in the fourth image, Sirius is now the small one, looking puny compared to stars Arcturus and Aldebaran. In image 5, Aldebaran is quite small compared to Antares and Betelgeuse, and even Betelgeuse is small compared to the largest stars we know. This picture serves to illustrate that when we look at the sky, most of the stars and even the planets all look about the same size, but they are far from similar. Their sizes vary tremendously. This image shows you that all the major planets are orbiting within the same plane, the original plane of the protoplanetary disk. You can see that Pluto's orbit is inclined or tilted about 17 degrees. It's not a lot, but many of these far-off bodies that we call Kuiper Belt objects are not orbiting within the same plane as the other planets. And at the edge of our solar system, we have two final regions. The Kuiper Belt is a torus-shaped area out beyond Neptune. A torus looks kind of like a donut. The Sun and 8 major planets orbit within the donut's hole, while Pluto and hundreds or thousands of other objects orbit within that donut in eccentric and inclined orbits. Remember, eccentricity refers to how oval-shaped the orbit is, how far from being circular. Inclination means that the orbit is tilted out of the plane of the major planets and the Sun. Even farther out is a giant sphere of material surrounding the outer solar system called the Oort cloud. This area is where many long-period comets originate, We'll talk more about these areas later on in this unit.